Okay, so I've already started drawing some stuff here. Excuse me. Okay, so you said that you were having issues with hanging string problems. So this is your hanging string attached to some solid surfaces. So there are two strings at two separate angles, and you have a mass which is applying some force. Let's make that smaller. Some force F sub g. So let's come over here, and the first thing you're going to want to do is, and you probably already know this, is draw your force diagram. So I've already drawn on there F1, which is from this string right here. And in a different color, I'm going to draw on your force number 2. Which is from the other string, obviously. And that will be at an angle phi. And this will be at an angle theta. And then, of course, we can't forget your downward force. What color is that? Your downward force caused by your block. And we're going to call that, predictably, F sub g. So these are all three vectors, and they're all pointing off in different directions. So F1, and here I should probably keep my notation consistent. F1 is a vector, F2 is a vector, and then F sub g is also a vector. And you can split these up into components. So the way you do that is, and again, you probably know this, I'm just repeating it for the sake of repeating it, is you'll have your x component, x comp, is going to be your magnitude of F1. So I'm going to leave off the arrow for to denote that it's a vector, because it's not a vector. I just want the magnitude, times cosine of your angle, which in this case is phi. And actually, I think I messed that up. It's not phi, I'm sorry, it's theta. Because over here we had, we denoted that as theta, so I'm going to change that real quick. And yes, I am using paint for this because this was very spur of the moment, and, well, damn it, I just wanted to make a video. So, okay. And now you're going to want your vertical component, your y component. Y comp is going to be F1 sine theta. And we can draw these on here because I can. Let's try to move that off the axis just a bit. And then we can call those the vector components. Excuse me. And let's go ahead and mark our axes here. Okay, so those are the vector components. Now, technically speaking, they do have a direction, because we've drawn them on our force diagram here as having a direction. However, this value here and this value here are by themselves not vectors. They are, because we have used the magnitude of F1. We've used the magnitude of F1 here in both terms, as opposed to the vector quantity. Oops. However, we could write these as vectors simply by adding the vector notation to the end. So x comp would be in the positive I direction. So we just add an I here, and then that would become a vector. Okay, so we do the same thing for the other one. So we can call this, well, the colors will differentiate it. So x comp, and I'm just going to put abbreviate that CP because I don't feel like writing it out. If I feel like doing any more of these, I'm going to get a tablet or something. Oops, an S in there. So I'm just going to copy this down. We're doing the exact same thing. Excuse me. And I'll choose a slightly lighter color, and we'll go ahead and plot these. So just to label this vector here is y component, and this vector here is your x component. Same with the components for the other vector. So now that we've done this, we can we have all of these vectors now in terms of their components along the x and y axis. Now, as you notice, these values right here, these values are both positive, even though your x value is pointing in the negative x direction. That's okay because, like I said, these are not vectors. These are just scalar quantities. If you wanted to write this as a vector, you would recognize that this is the negative x direction, and I hat is, if you don't know, is the unit vector. Is the unit vector in the x direction. Okay. And just to fill in this little piece of information here, I hat is the unit vector in the x direction. You also have j hat, which is the unit vector in the y direction. I'm abbreviating all this because I don't feel like trying to write it out. And then you also have k hat, which we will not be using because this is two-dimensional, which is the unit vector in the z direction. That's not legible, but you have this video, so I don't really care. Okay, so if you're trying to look for, say, the tension in one of these ropes, that's going to be the force. The force here is going to be your tension, because tension is a force, and so we can call this tension 2 and call this tension 1. And if you're looking for, say, tension 1, what is the total force that this rope right here is applying on this block of mass to keep it from falling, obviously, because I mean it's not going to fall here if it's hanging from a string, right? So we want to find, let's say we want to find F1 or the tension in this rope. So how do we do that? Well, we need to know. We need to be able to find the components of the vector F1, because we know that F1 is, if we move our component over here, we can form a right triangle. which is where we get this stuff from. In this right triangle, so this would be x comp, and this would be y comp. Okay? So that's where that comes from. And because we know the components, I'm sure you've used vectors plenty of times before. Or if you haven't, you can yell at me for making that assumption. And you know how to combine components into a vector. I mean, you've taken Calc 2, so, and I think you do that at the end of Calc 2, right? Or something like that. But anyway, so okay. So anyway, so we have equations here along the x and y axis. Clearly, the force of G is only directed on the y-axis. So we can actually pull a component from here. Let's do that in yellow. We can actually pull a component from this force vector. I'm going to move down here. Force of G. This vector is, if you've seen vectors written in component form, is going to be 0, negative f of G. So these are just, so if we were to write f1 in component form, we would just have f1 vector is equal to f1 cosine theta f1 sine theta, and that would be our component, or those would be our components in vector form. So because this points only down in the y direction, we have our x component here. Again, let's do this in yellow. We have our x component here and our y component here. And as I said, it's only pointing down in the y direction, so we can just say, okay, that vector has a y component of negative the vector's magnitude, which makes sense. If it doesn't make sense, you can yell at me. But anyway, so we can pull that component from here. So now we have everything in their components all along the x and y axes, and the nice thing about mechanical systems is that they obey a law of superposition, where the x and y axes act as separate systems. So if you throw a ball horizontally, it will only accelerate vertically. Gravity has no effect horizontally, at least close to the Earth's surface. But I digress. So we can add components along each of these coordinate along each of these coordinates. So anyway, so we're going to get two equations. We're going to get one for the x direction and one in the y direction. Let's set these up a little bit better. So we're going to get a x direction, and we're going to get a y direction. Let's spread these out a bit. Let's just look at the x direction first. So we're going to look at the total equation in the x direction. Yell at me for going too slow here. I'm sorry. I'm kind of tiptoeing around talking right now because it's currently 1:15 in the morning. So trying to be as respectful as I can. But anyway, so we have two components here. We have the x component of f2, and then we have the x component of f1, both pointing in the x direction. So we're going to combine those. We're going to add those together because we can do that. We can add two scalar quantities and the universe will not explode. So I'm going to write down, we have x component of our f1, and then we have our x component of F2. And now what does that equal? Well, if you look at your system, you have to ask yourself, so force by Newton's law, force equals mass times acceleration. And I'm going to change that around. Mass times acceleration. So we obviously have a mass here. But our real question is it accelerating? And for this system, we have a hanging mass. So it's not going to be, it's not moving, right? It's stationary. It's not accelerating in any direction. And we're looking at a horizontal acceleration in this case, because these are two forces. So we have two forces, and there's no acceleration. So they're going to add up to be 0. We can change this around and say that because of this, the x component of F2 is going to have to equal the x component of F1. So let's rewrite this with the actual components in here, and we'll have F2, and the x component was cosine theta, I'm sorry, cosine phi, is equal to F1 cosine theta. So that's going to be important because that's a nice simplifying equation there. We have just equated F2 and F1. So now we have to find, but now we want to find F1, so we can actually solve this equation for F1. We can write F1 is equal to, we can just divide both sides by a cosine, and we'll get F2 cosine phi over a cosine theta. Okay, and I just noticed I have no idea if this is recording my voice. So if you're not hearing anything, or if I play this back and I'm not hearing anything, then I may have just wasted a bunch of time. But oh well, I don't care. This is keeping me from doing my physics homework, so you know, bottom line, I'm happy, kind of, because my physics homework's kind of overdue. But anyway. So we've now solved for F1, but we've solved for it in terms of F2, and we're not entirely sure that that's a value that we want. We're probably going to be given a mass, and from that we can derive this term of Fg. So we want to include an Fg in here because that's probably where our terms are coming from. And to do that, we go to the y component. So now we're going to look at the y direction. And going back to the reason that we can do this, it's because physical systems are not codependent. In a Cartesian coordinate system, you have horizontal and vertical components act separately and are independent from each other. That's why you can do this stuff. If they weren't, then this would be a heck of a lot harder. And frankly, it would be a pain in the ass to do, and I would be surprised if physicists were still sane. I mean, technically, I guess they're not, but still. Anyway, so here we have two different things pointing in two different directions. Oh, that's one thing. We have xcp here is in the negative direction, right? So if you wanted to, and I think this is where your issue's coming in, you can treat these like either scalars or like vectors. Here I treated them like scalars. So I solved for F1 and F2 cosine phi over cosine theta. I solved for it as if they were scalars. You can do this as if they were vectors because they're in the same direction. And you can add vectors. If I have a vector here of a total distance of 1, or make it easy on ourselves, it's the vector 1, 1. I can very easily add to that a vector of 1, 0. I just get a vector of 2, 2, 1. So you can add components of vectors and not have to worry about any silly interference from the other components. So that being said, we can treat these as if they were vectors, in which case I would just add a negative sign out in front of this one because it's pointing in the negative I direction, so that negative sign is coming from here. And then I'd come up to my other component, and that's pointing in the positive I direction. So I just add an I. And now I just turn my components from scalars into vectors. Yay! So now I can come down here, change that, make that a negative, make that a negative, make that a negative, make that a negative, and make that in the I direction, and voila! Well, actually, this is not correct. That's actually not correct because F1 is clearly not pointing in just the I direction. So what? I'm sorry. You can't treat these explicitly as vectors, but you can treat them as, I guess I can call it pseudo-vectors. Sorry for that. So what you can do is you can say, instead of xcp being a positive value in the negative direction, you can change that, and I can actually draw that on here. You can say that it's a negative value in the positive direction. So that way you have both of your vectors pointing in the same direction, and then you can include this negative sign down here. So you can do that, but I'm not going to because that's silly, and I already know, there's no acceleration. So my final, my final vector here is 0. There's a 0 acceleration in the x direction. And anyways, I'm just interested in the magnitude of t. I already know the direction because I'm probably given theta, and if not, I mean, finding theta is only a couple steps more, depending on what you're given. So, okay. Oops. So, okay, so now in the y direction, we have 3 components, right? We have your y component of f2, your y component of f1, and then you have your negative fg. And because those are on opposite sides, they're working against each other, right? Excuse me. So now we have to come back over here to the force equation again, and we have to ask ourselves again whether or not this is accelerating in the vertical direction, which it clearly isn't because it's not moving. So we're going to have a net acceleration of 0 again. And now we just add up all these vectors. So I'm going to throw in my f sub g. Oops. Plus my y component there, plus my y component there. Now you could also, because this is pointing in the negative direction, and I will actually do it this time, change this to a negative, that looks weird now, but a negative vector in the positive direction, which I I will now treat this as a negative vector in the positive direction. Because that makes more sense, because, I mean, the magnitude of f of g is going to be positive. Its direction is negative, but its magnitude is positive. So I'm just gonna throw this in here so that, so the math gets a little bit easier. Namely, because now I can pull this to the other side, and I can say that fg equals, I'm probably doing a lot of unnecessary steps here, but that's just because my thoughts are sporadic and I'm plagued by fits of insanity, but that's besides the point. So anyway, I can pull this to the other side here, which is pretty intuitive. I mean, if it's not moving, f of g is clearly going to be equal to the sum of these two. Excuse me. So that's what, we'll get that. And now I'll go ahead and add in my my actual components here. So I have f2 sine of phi plus f1 sine of theta, and that's just going to be equal to whatever my magnitude is of g. So that's actually, if we come back up here to f equals ma, we'll actually find that this is the mass of the object times the acceleration of gravity. So now, because we've solved f1 in terms of f2, I'm going to solve this equation in terms of f2 as well. I'm sorry, in terms of f2, so I can plug that into this equation and get one equation for f1. So I'll go ahead and rewrite this as mg minus f1 sine theta. And from this point onward, it's all really just algebra. And that's going to equal f2. So we see that when we plug that into here, we're going to get a term of cosine over sine, which, if you know what cosine over sine is, that's going to be cotangent. So surprise, surprise, this is dependent on your slope. So we're going to get a term of that. So I'm going to rewrite this and combine these terms now. So f1 is equal to, I'm going to pull out my mg minus f1 sine theta, and I'm going to put that over this cosine theta from over here. And then I'll have my term over here of cotangent. And that's going to be a cotangent of phi. And now, if you take notice, we have a term of sine theta over cosine theta here. So we'll actually get, if we simplify this further, I may have to expand my workspace here. If we simplify this further, we're going to get f1 equals mg over cosine theta, because that term is still here, minus f1 times a tangent of theta. And then we'll have this whole thing multiplied by a cotangent of phi. So now this looks a little bit messy and triggy and whatnot, so I apologize for that. But nonetheless, we have this in a form now that we can reduce further. So I'm going to rewrite this up here as f1 equals, and I just realized that I think I'm recording. I think when I show this, you should be able to see everything, but in case it's like really zoomed out, well, I guess you can still kind of see stuff here, but you know, we'll see what happens. First time using new software is always fun. So f1 equals mg over cosine theta and I'm actually going to take a step in here and I'm going to multiply this by the cotangent of phi. And then, you know, I'm going to distribute that term to both of the terms. So when I come back up here to rewrite my negative f1 what is that, tangent theta, I'll also include my my cotangent here of phi. And now if you notice, I have two f1s here, and my goal is to combine those. So I'm going to move this to this side by adding that term, and I'm going to skip a step and pull out an f1, which will give me f1 times 1 plus, if I pull an f1 out of this term, I will get a tangent theta, cotangent theta, I'm sorry, cotangent phi, equals mg over cosine theta. So now we're just one mathematical algebraic step away from being completely finished here. So now I just want to isolate my f1 by dividing this whole side by this term. By this term here. So it's gonna look a little messy, but you know, it's physics. It's supposed to be messy. We're doing science here. So we're gonna divide this. We're gonna get cosine theta over. I'm gonna write my constants in a different color here. 1. Because it doesn't, you know, it doesn't look that great when they're the same color as the operator. So 1 tangent theta, cotangent theta, and that is going to be your answer. Now, as a quick aside, let's say that these strings are mounted at the same point, and you're introduced a new condition, and I'm going to cycle through a lot of colors here. Your theta is equal to phi. Well, you know that tangent theta times cotangent theta, because they're inverse functions, or because they're, you know, the inverse of the other, those are going to cancel and become 1. So this whole thing down here is going to simplify significantly, and you're going to have the final result of F1 equals mg over 2 cosine theta. Whew. And actually I'm going to write that in purple because why not? And then that would be your answer. Let me check my my arithmetic here. You know, if you see a problem, don't hesitate to tell me and let me know. Okay. So this has been a Michael Schott original. Thanks for watching.